Hello everyone, this is Professor Zhengguang Liu. It's my honor to share our ideas with you. Our paper title is Smart Contract Vulnerability Detection Using Graph Neural Networks. This is an AI plus blockchain practice. Nowadays, blockchain is very hot. Blockchain is essentially just a ledger maintained by multiple parties. Each party has a copy of the ledger, making it hard to tamper or illegally modify the transactions in the ledger. So blockchain is not that complex, it's just a safer ledger. It's safer because since copies of the ledger are stored by multiple parties, if you want to change the ledger, you need to persuade more than half of the parties to have the same fake ledger as you, which is very difficult. Then what are smart contracts? Smart contracts are programs or codes running on the blockchain. What is the difference between smart contract and conventional programs? The difference is that smart contract is running on the blockchain, so it is shared by multiple parties and cannot be modified once it is deployed on the blockchain. A smart contract defines contract terms or rules to manage digital money. Using smart contracts, we can implement contract terms into codes and run it automatically. For example, there is a football match between Barcelona and Real Madrid. You and me have a bet. I bet $100 that Barcelona will win, and you bet that Real Madrid will win. We can implement it into a smart contract, which has three contract terms. The first term is that you and me both send $100 to the contract. The second term is that the contract obtains the final results of the match from an official and reliable media. The third term is that if Barcelona wins, the contract sends all the money to me, and if Real Madrid wins, it sends all the money to you. Since the smart contract is code that will execute automatically on the blockchain, and no one can modify it after its deployment, the contract is fair and automatic for both of us. Millions of smart contracts have been deployed in various blockchain platforms. This enables a wide range of applications, including wallets, crowdfunding, and finance. Smart contracts now hold more than $10 billion worth of virtual coins. Undoubtedly, holding so much wealth makes smart contracts attractive enough to attackers. So far, smart contract vulnerabilities have caused more than 200 million US dollars loss. For example, in June 2016, attackers used the reentrancy vulnerability of the DOR contract to steal 3.6 million Ether, which was worth 60 million US dollars. There are two reasons that make smart contracts to have bugs. First, the programming language of smart contracts are still new. Developers are unfamiliar to the new languages and may write code with bugs. Second, since smart contracts cannot be modified once deployed, developers are required to anticipate all possible states and environments the contract may encounter in the future, which is definitely difficult. Therefore, smart contract vulnerability detection before the deployment of a contract is very important. How do current methods detect smart contract vulnerabilities? Current methods rely on fixed rules to detect vulnerabilities. That is, we predefine several expert rules to detect a vulnerability. If the contract codes fulfill these rules, then a vulnerability is detected. Otherwise, if the rules are not fulfilled, The contract does not have a vulnerability. However, there are some complex cases where it is hard to define several rows to cover them, and attackers can bypass the fixed rows easily to perform attack. The second problem of existing methods is that they do not extract reads, control flow, and data flow semantics from the codes. They transform the codes into control flow graph, but their tools are very coarse, and all program elements are usually treated as equally important. However, it's obvious that some program elements are more important than others in detecting vulnerabilities. Therefore, in this paper, we try to solve two challenges. Challenge 1, how to extract the reads, data flow, and control flow semantics from the codes. And challenge 2, can we do not use the fixed rows to detect vulnerability? For example, deep learning is very hot. Can we use deep learning methods to solve this problem? There is still no effort that tries to use deep learning methods to detect smart contract vulnerabilities. We are curious whether it can work on this task. The problem is simple. Given the source codes of a smart contract, we are to detect vulnerability at function level. That is, given a smart contract function, we are to estimate the label y, where y equals to 1 means that the function has a vulnerability of a certain type, and y equals to 0 means that the function has no such vulnerability. In this paper, we studied 3 types of vulnerabilities: reentrancy, infinite loop, and time-step dependence vulnerabilities. This figure shows a simple example of reentrancy. There are 2 contracts, the bank contract and an attack contract. The bank contract has a reentrancy vulnerability. The bank contract has 2 functions, deposit and withdraw. We can first deposit $10 in the bank contract. Then we can withdraw the money by using the withdraw function. The 8 to 10 lines of the bank contract shows how it transfers money to us. First, in line 8, it reads out how much money we have in the contract. Then, in line 9, it transfers the money to us. After transferring the money, the contract reduces our balance to 0 in line 10. The balance reduction is conducted after money transfer, which can cause the reentrancy bug. That is, when the contract transfers money to us, the fallback function of our contract will automatically be invoked. In our fallback function, we can call the withdraw function again. Since currently our balance is not reduced to 0 yet, the bank contract still believes that we have $10 balance, so it will transfer $10 to us again. Therefore, we can obtain $20 even when we have only a $10 balance. Actually, we can call the withdraw function several times to steal more money. This vulnerability has caused the dog event, where attackers steal $60 million. The second vulnerability we study is time-step dependence vulnerability. What is time-step dependence vulnerability? For example, you and me have a bet on the last number of a block time-step. If the number is even, you win, and if the number is odd, I win. If I were a miner that has the right to record this block, I actually have a 900 millisecond freedom on the block time step. I can cheat by making the last number of the time step be an odd number so that I can win. This is called the time step dependence vulnerability. The third vulnerability is infinite loop. Infinite loop means that there may be an infinite loop in the smart contract function that never ends. For example, a while loop or a for loop that never ends. Unlike conventional programs that only consume computer CPU resources, smart contract needs to pay for the execution of each line. If your function has an infinite loop, you are unable to successfully do anything, but your money is spent. Our method has 3 key steps. In the first step, we transform the contract function codes into a graph where the nodes represent function calls and variables, and the edges models data flow and control flow between nodes. Different smart contract functions will produce different graphs. Some graphs may have 6 nodes, some graphs may have 3 nodes, and some may have 13 nodes. It is hard to train the graph neural network if all the graphs have different shapes. At the same time, some nodes are more important than other nodes. For example, call.value invocation is a key to detect the reentrancy vulnerability. So this invocation is much more important than a normal function invocation. The program elements should not be considered as of equal importance. Therefore, in the second step, we normalize the graph to highlight the key nodes and remove the non-important nodes. Non-important nodes are removed, but their features are merged to their nearest key nodes. In this way, all the graphs are normalized to standard graphs, which have a fixed number of nodes, usually 4 nodes. In the third step, we input the standard graphs and their corresponding vulnerability labels to train the graph neural network. The network will learn how to determine whether a graph has a specific type of vulnerability. Here, this figure shows an example. The left side are smart contract source codes. The contract has 2 functions. We are to estimate whether the first function has a reentrancy vulnerability. We first transform the function codes into a contract graph. Then we normalize the graph into a standard one. Finally, we apply graph neural networks to the normalized graph to give a label. We use a temporal message passing network as a graph neural network. The network works by passing information along each edge in the graph. In each time step, it passes information along one edge. In the first step, it passes the information using edge 1 and updates the states of the nodes connecting to edge 1. And in the second step, it passes the information using edge 2 and updates the states of all the nodes connecting to edge 2. And so forth. Note that each edge has an order. The order corresponds to its appearance order in the code. After passing the information along all edges successively, we read out the final results and the original results of all nodes and filter the states using a fully connected layer to give the final label. We have conducted experiments on all the smart contracts that have source code in the Ethereum. We also conducted the experiments on another blockchain platform, VNT chain. In the Ethereum, there are 40,000 smart contracts, which have around 300,000 functions. Interestingly, in the very beginning, we have tried not to transform the codes into graphs, just directly input the codes into an LSTM network. The results show that it performs quite worse than conventional tools. However, if we transform the codes into graphs, normalize the graphs, and use graph neural networks to handle the graphs, we are able to outperform existing methods by a large margin, improving the accuracy from 71% to 84%. We find that the main reasons are twofold. First, the existing methods indeed rely on fixed rules or patterns, which may not be that effective. Second, they do not extract the reads, data dependency, and control dependency semantics from the codes. In conclusion, overwork is an exploration on whether deep learning can be used in smart contract vulnerability detection tasks. The results are positive. Our datasets and codes are released in GitHub. You can also contact me to get them. We welcome you to join this exploration. Thank you.